What's that?
I didn't practice with matrices at all.
Well, there you go, man. You knew what you were going to get before you even did it. So last time we just barely kind of did an overview of all of chapter 11. What I'm going to do, we're going to focus on 11:1, 2, and 3. Let me see if you guys can handle what I'm about to say. 11:1 through 11:3, that's definitely going to be due Tuesday on the day of the test. I'm going to let you have 11:4 until the final. If you get done with it earlier, you can always turn it in a course. You guys with me so far?
Just double check it.
It's on the sheets.
Oh, yeah, okay.
Yeah.
Sure that's right.
Put them on all the sheets just because I know it's not going to stay in there. Okay. Cool. Let's see. So we went pretty quickly over just the basic idea behind each one. So now I want to get to the nitty-gritty of how to actually do each one. So this is a very different way. Let's start with parabolas. It's a very different way to write. Let's start with the kind of parabola we're used to. Okay, cool. There it is. And real quick, as we're getting into this, there's like a parabolic orbit. Come, there you go. Yay. So the neat thing about parabolic orbits is they're called escape orbits, but well, they're actually not called escape orbits. They're at the minimum escape velocity is what would put you into a parabolic path. So if you don't have the escape velocity, of course, the Earth would suck you in, and you just kind of either crash into the Earth or just orbit the Earth. You with me? So this is going just fast enough to not have that happen. So what happens, though, is it loses almost all of its velocity as it goes out, maybe even all of it. So it just kind of goes and just peters out and goes, eh. But if you're on a hyperbolic, it looks the same. Parabolas and hyperbolas look the same. But here's your hyperbolic one. And it's just a little more, it's less rounded, right?
Yeah.
So there's actually a little more velocity that's in your favor. So that's how this gets set up. It's not as circular because it's not being as affected by the gravity because you're going a little bit faster. You're going at, this is called the escape orbit. You actually escape it and you actually have some velocity left. So you can actually get somewhere else, right? If you are a planetary or heavenly body, right? Something going around the Earth. Oh yeah, thanks, Megan. So we're used to seeing stuff like that. Can somebody tell me? Do you guys remember? Would that make this parabola? What would that do? That 4? Make it skinny because it's a lot like a slope. So it's going to rise much quicker on both sides than it would have. So that makes it skinny. To make it fat, I have to put like 1/4 over there, right? Is that in that form?
No.
All right, good. Helen. So then how would I put that into that form?
Isolate the x squared.
Yeah. So your x squared equals. So here's where things get interesting. This is where students, that's why I wanted to start with this one, because people think P is 1 here. But it's not in the right form to see what the hell P is. Now, can anybody help me out? Is it in the right form yet?
No.
No. I gotta write x squared equals 4 times something to be 1/4, and that would be 1/16. Kick ass. Alright, so that's the first thing to realize about these. This kind of new way to look at parabolas is it's got to be in this form to tell what P is. And what the hell is P all about? Does anybody remember?
Focal
It's related to the focal diameter, right? So the focal diameter would
It's
be
the shortest point. Right?
twice that.
Is it the shortest point?
Good.
From, like,
Good. So it's where the focus is. The directrix would be at negative. Probably is negative this. So P is 1/16. The directrix would be at y equals negative 1/16. The vertex would be at 0, 0, of course, because this is not shifted, right? So this distance here is
1/16.
1/16. So of course it makes sense that in general the focus
Would be 1/16 away
is
from
0
the
p.
focus.
The directrix is back p and the focus is forward. And then that automatically sets up the base case of it's the same distance on either side. You kind of look. So that's that close. Like Chris said, it's the closest approach in a way, right? Like the Earth, and well, in the earlier example. And then so here's my focus. It's going to be at 0, 1/16.
Why is it negative 1/16?
Because it's the direction.
Because it's got to be on the other
Oh,
side.
that's an imaginary straight line.
Exactly, the directrix. And then to do this, the easiest way to do this is to realize that I know where two other points are. I already know, based on something Carter said earlier. What is the focal diameter?
2p.
Yeah, in general it's 2p.
Absolutely. So 1/8.
So it's 1/8. So then there's got to be a point that's 1/8 over from here, right? And then there's got to be a point that's 1/8 in the other direction. So of course, what points would those be? Yeah, so the x pieces will be 1/8, negative 1/8.
And then one.
And of course it'll be, so there'll be a point right there, and there'll be a point right there. So it's kind of a trade-off. It's a little more complicated, we're not used to this. But then the minute I put it in that form, I can see P, and then P gives me the 2 points automatically. I don't have to plug anything in, I just get them. Okay, cool. Yes, ma'am.
Just wondering why again, how does x squared 4py go to y equals 4x squared? Like, I understand why you lost
No,
it.
so here's like y equals mx plus b. That's the form for a line, and if it's in that form, I know stuff. And then here's a problem as they give it to me. And I go, oh, that's not in the right form, let me put it in the right form.
Okay, got it.
I'll lock it. Alright, not too bad.
So is there a specific name for that form?
I think the book doesn't really, no. It's not standard form, because standard form is where you can see the vertex. Yeah. So we'll call this the P form. Now, included in this whole package deal is parabolas that open sideways. Right? So their equation is just going to look like y squared equals 4px. So if I had y squared equals 8, gather p, 8x.
So it's
Square root.
No, don't do any of that stuff.
4 times 2x.
I know this is going to be, so what effectively, what, if I have this equation, how can I make it look like that? I just switch the x and y. So wouldn't that be the, kind of like the inverse, right? But now we're allowing the whole damn thing to exist. I'm not talking about an inverse. I'm just talking about a parabola that happens to want to open this way. But it is related to the idea of inverse. I just switched the x and y, didn't I?
Yeah.
So please don't solve for y. We are now working with things that are not opening up and down, but opening sideways. That's all. Everything still applies. What's p here?
2.
Yeah, p's got to be 2, so if I put it in the right form, I know p is 2. But now since it's opening left and right, where will the directrix be?
On the y-axis?
A lot, well,
Well, onto the left of the y.
parallel to it. Yeah, the directrix is going to be at
Negative 2.
x equals negative 2. So the directrix is always a line. Yeah.
Just a quick question about the x squared equals 4py. Is that a base equation, or is that just...
That's the base equation for this type of
So
work.
whatever it has to be times
So if
4 times whatever.
Exactly. I like it.
So it'll always be...
Yeah, that's what it says.
Find p and make it 4p. Or is that just...
Yeah, exactly. So here, there's an 8 there, so what would p have to be in this form to make it 8?
2.
2. So I want to write it in the form 4 times some number times x. That'll make this true. So p must be 2.
Why 4? Because
That's
four
Is that
words.
just for this equation?
Well, I'm desperately trying to not go through the derivation for this. I just want you guys to accept it.
So it's just four, no matter what.
Just always for.
Yes, it's just always.
It's just for right now, so.
Okay.
And the way you do it, and I think the book, actually, I can't remember now. But yeah, the book goes through the derivation. And again, it's just starting at the definition. What was the definition for a parabola? It's a collection of points where this distance, the distance from the directrix, is the same as the distance to the focus. So if you just write math equations, we sort of started doing that the other day for a circle. We did it all the way out because a circle is the easy case. But you do it the exact same way. You say, here's a point, x, y, and you call the focus 0p. And then you have this distance, you can figure it out using the distance formula. And then you have this distance, you can figure out using the distance formula, and you set them equal to each other. So you can follow that through in the book. And that in the 4 just comes out. It's not somewhere they go, let's choose 4. No, it just comes out of the math to make this true. So from the definition of what these points must do, they must be equidistant from the line and the focus. The math gives me this. Bam. And I go, thanks math, whatever. So now I know that for this problem, P is 2. Since I'm opening this way, what would make it open that way, of course?
Negative.
If it was a -8, I lock it.
Mm-hmm.
Or if there's a negative somewhere in there, yeah, sure. Because it would just come over there. So what else can I use this for?
Focus and the focus.
Yeah, the focus is going to be at
2.
And I don't, you just put like a little open circle there because it's not a point on the parabola, right?
Yeah.
That's just a kind of a, it's kind of neat if you push it in, if you push the focus in. Let me remind you, is that focus length longer than this one, right? Definitely, big time. Because this is only 1/16.
Mm-hmm.
And this was a really fat, no, I'm sorry, skinny. Okay, good. Yeah. It was really skinny, right?
Mm-hmm.
So it's kind of cool. If I push this in, my parabola goes, and if I pull it out, my parabola, oh, thank God.
Mm-hmm.
Does that make sense? So if I push the focus in, it goes, oh shit. And then if I pull it back out, it's like, oh, okay. Alright. So, what's going to be the focal diameter here? Yeah, it's twice p is 4. So at the focus, I can just go, well, it's 4 across. So to me, the radius is always better anyway. But I want to go up and down 2, so that overall I get 4. So that gives me automatically these 2 points. What are those 2 points?
2, 2, and 2, -2.
Yeah, 2, 2, 2, -2. Yeah.
In the other one, you had the difference of 1/8. And that was after you multiplied. Why is the focal diameter?
Yeah, the focal diameter is always twice the p. Focal diameter is equal to 2p.
Why is those 2 points not 2, 4, and 2 negative?
Because the total distance is 4.
Yeah, the diameter is 4, right? This is
I
kind of
got
like the center for that.
I got you.
Does that make sense?
Yeah.
Okay, cool. So it's the same thing as this, just rotated. Okay. Maybe. So then, and then you have this is 0. So then you have this here. Yeah.
So on that other one where it's 1/8 and the focal, isn't that shouldn't that be the focal diameter is 1/8? Yeah. So then it wouldn't be 1/8, it would be 1/16. 0 would be 1/16, 1/16.
Oh yeah, so here the focal diameter was twice 1/16, which is 1/8.
So then you have to
Yeah,
change
so
those
this should
points.
be 1/16 and 1/16. I like it. So the focal diameter is for constructing a parabolic satellite dish or something. So you know exactly how long it's got to be across. But for the purposes of graphing, I always prefer just to look at P as my radius. Just start at the focus and go up and down that much. So P is 2. So I'm going to go up 2 and down 2. Okay. Let's see. So that's, they do up and down on page 725. They do left and right on page 726. And they talk a little bit about, we talked about this yesterday, about how you can use it to focus light. You put something at the focus, it'll push it back out straight. So that's how you make spotlights and all that kind of stuff. Okay, cool. All right, so that's parabolas. Nothing too major. I'm trying to focus today on hyperbolas because they're the freakiest ones. Parabolas are different, but they're not that difficult. Ellipses are not too evil, believe it or not. So, the main form for an ellipse is this guy here. So whatever you're given, so yesterday we got one, and we'll do this one first because it's an evil one. I don't know if you guys remember, but yesterday we looked at this guy here. We talked a little bit about this. So why is that not really in the right form? And this will also help us with the question I was asking yesterday. I was trying to ask you which way is it going to be shorter, which direction is it going to be shorter. So
It doesn't have over A or B.
we did parabolas. Yeah.
It's not.
Yeah, so it's not in this form. Now I'm going to force it to be in this form here.
Put it over 1/3 squared.
Yeah, I like it. So it's going to be over 1/9. Y squared, of course, is over 1. And I don't want to do anything to both sides because I have to have a 1 there. So, of course, if you have something that you're pretty sure is an ellipse and it's equal to 16 or something, you divide by 16. You have to. That's the most important part of this form is to get a 1 around.
These are ellipses, right?
These are ellipses. I know this is an ellipse because,
X squared and Y squared.
good, two things. So it could be a circle or an ellipse, but it's
Got the 9.
different coefficient and it's a sum.
Okay.
We'll put a minus there, now we're talking about hyperbola. Yeah. Cool. So here's the nice thing here. This is kind of nice. If y was 0, x squared has got to be 1/9 to make it 1. So in general, whatever this is underneath is the square of the distance you go out on the x-axis. So if I say a squared is 1/9, a is 1/3, I'm going to go out 1/3 up and down on the x-axis. Because think about it. For x equal to 1/3, y would be 0. It has to be. Because if I let x equal 1/3, what do I get? 1/9 divided by 1/9 is
1
already. So y has got to be 0 to get the hell out of the way, right? You guys kind of with me?
No.
So again, if x is 1/3,
squared.
1/3 squared is 1/9. 1/9 divided by 1/9 is 1 already. Can y be anything other than 0? No. And you can do the same thing with y. If y is 1, that's 1 already. X has got to be 0. So that's why these numbers directly control where those points are going on the axes. That defines how my ellipse is shaped. So in this case, it is going to be like this, because it's not going to be as far out on the x as it is in the y. So if I want to go graph this, here's the beauty of this. Once you put it in this form, which should be relatively easy, all you got to do is take square roots of the bottom. So here b, of course, is 1. I'm not doing plus or minus because these are lengths. And you could do plus or minus because you got forwards and backwards, whatever the hell you want to do. I know it's at 0, 0, y, the
Because
center.
There's no shift.
The sort of center. Yeah, there's no shifting here, right? So I know it's 0, and so I want to go back 1/3
So
and forward 1/3.
So A is your X, B is your Y.
In this case, yeah. And I think I made the handout just like the textbook, but to be completely honest, who gives a crap what you call this guy? They switch it for the hyperbola and all that kind of business, but the A affects the X direction and the B affects the Y direction. Why? Because that's who they're with, right? For both hyperbolas and ellipses. So I hate the fact that they're so careful with their A and B. I understand they have to be, but you don't have to be. A is with the X, so it's going to control the X direction. So how far am I going to go on the Y-axis? Yeah. 1. Big old step. And then you just fill in as best you can. Obviously, I'm not going to grade you on artistic ability. That would be the height
These are
of...
supposed to be plus or minus, right? Since we square root them.
So again, it's a length. It's a length. It's a length. So it's not negative. Yeah. It's a distance away from the middle. So I'm not going to take the negative part. Cool. Now, there are still foci here, right? So if I look at the ellipse on here, and Wikipedia, this is Wikibooks actually, but Wikipedia's, oh, good job, John. I didn't want to show you that. Shoot. I think the history here is all screwed. Parabolic orbit. There we go.
So this thing was football, right?
I want orbits. What's that?
Did you say so this thing was football then?
Really? Alright. I lost my poor little animation. That sucks. It's too bad for us. Orbital and can't do that. Anyway, so for the Earth, the sun is at one focus. Here we go. This is trying to be it, I think. Let's pretend. So the sun is at one focus, and the other focus is empty, but that's how we travel elliptically around the sun. That's very, very close to circular, which means the two foci would be really, really, really close together. So the sun is not that far off the center. But we are in a circular orbit because it is not right in the center. Okay, cool. So how do I find the foci here? Here's how I remember this. This is a little bit evil, but only if you let it be. The foci have to be, where do you think they have to be? The foci. Inside or outside? Inside, because it kind of goes along with the idea with the parabola, when you push it towards it, like, oh. So I know they're going to be like roughly here and there. This is pretty elongated, so they're not really going to be close to the center. Are you with me? So the location of the foci is, in this case, is going to be 0C. We use the letter C. And here's how you find C. Here's the semi-evil part of this. In this case, well, screw it. This is another reason why I don't care about the A and the B.
Foci.
Because there's two.
Yes. Foci. And I think for ellipses, if I'm not mistaken, yeah, again, okay, so I'm already going against what this thing says. For ellipses, it calls A the bigger dude, right? It calls B the little dude. So it would make this B squared. I always just made the thing under X A squared. And again, because it doesn't matter, whatever one is bigger is going to go first, or else you have some imaginary focal length, which is really neat. Let's not do that. So I would always just say, okay, Pythagorean theorem is this.
Yeah.
That's going to be true for hyperbolas. What's really nice is, what does a hyperbola have in its equation? Minus. So minus goes with plus. Plus goes with minus. Right? And I just always make this a squared minus b squared, so it looks more like the Pythagorean. It's just got a minus in it because it goes with the ellipse. They each only get one plus and one minus. That's one way to look at this. So how would I find the focus? And again, it makes sense for an ellipse. It's got to be inside. So I want to subtract to bring it back in. So then my focus, I can find it by, here's my a squared, which is, I'm going to use the bigger one, right? Bigger one first, minus 1/9. So c squared equals
Square root of
8 ninths. Yeah, so c is square root of 8 over 3. 2 rad 2 over 3. So that's going to be the focal length. What is that roughly? So we have a 20 divided by 3. 0.9. 3. Huh? 0.94. I got close. So in this case, it'll be 0.94 and 0 negative 0.94. So it's much closer to this vertex than it is to the center. Right? So of course, if I pull those in, this would become, what would happen to this if I pull these in?
It would become
It would
flatter.
become more circular.
More circular, exactly. Or fatter. Yeah. You're in shape. Circular. That's nice. It is a shape, exactly. All right, so here, let me let you guys try one on your own. Yes.
So what was that to do with that?
So with parabolas, the focus is the first thing I find, right?
Oh,
And it's very simple. But there's still foci here.
okay.
Because again, like I said, the sun is at one focus, and they're really close together, and that's why we're almost circular. So the foci, I just like saying it, are a huge part of what you have to find to make sense of this graphically. So this is how you find it for an ellipse. If I had a hyperbola, I would do it this way.
Okay.
And again, the way I remember it is hyperbolas have a minus in them already, so this guy's going to be a plus. Other way for the ellipse.
What was it you were saying about the bigger number underneath the x squared or something like that? You said.
Oh, so when you do this equation, you put the bigger one first. I don't care what you call A and B. And the book tries to make it match all the time, but you just put the bigger one first. Right. Yes.
I just forgot. Never mind. Oh yeah, what's the importance of the foci things? What's the importance of them in that? I mean, like, what do we need them for?
So for if you see something that's in an elliptical orbit, and you can figure out from its path what the equation would be, you can figure out what the focus would be, and you can figure out, well, there must be something at one of those two foci that are making it do that. And maybe it's something that is made out of dark matter, or maybe it's something, a dark star, or something I can't see. So then I go, maybe there's something there. Weird, cool. You kind of with me? I know you're not going to become an astronomer necessarily, right? And then I'm not going to tell you how it's going to help you buy lettuce. But in general, it's a good. I have to figure out what this is because it's a part of the reason why this looks the way it does.
Oh, okay.
Right. So a very higher level concept of that. How does it help me graph this? Not at all. I graphed the damn thing before we even talked about it, right?
Yeah.
But it's got more importance than just that. Yeah.
So when you're doing that, since with the foci at the 0.94, since it's just 0.6, would focal diameter still work? That is the same way, like
sort of. But in this instance, the focal diameter you don't. That's really reserved just for parabolas. Here, there would be no reason for it. I mean, the parabola, the focal diameter actually points to 2 points that sit on the parabola. Here, they just pointing to themselves. I mean, do you see what I'm saying? So the focal diameter is the diameter to the parabolic points at the focus. So here, there really is no idea like that. Because there's two foci, so it's a little weirder. Don't go all there. You don't have to go there. There's no diameter stuff here for the focus. Alright, so let you guys try one out. So here. Oh, sorry. Yeah, sure. X squared plus y squared. 16y squared equals 16. So I want you to find and there's some terminology here. The longer length is called the semi-major axis length. And the smaller length, remarkably enough, is called the semi-minor. It's crazy. Axis length. How important is the terminology? Really not as much. Is it equal to the right thing?
You have to.
So 4 and ellipse. It's got to be equal to 11. It's a little bit easier than here. Just make it, do what you got to do to make it equal 1. Just make sure everybody's on the right first step here. It's not like this one. This was kind of an ugly example to do, but I wanted to start there to show you how ugly. Yeah, this is nowhere near as bad. But what's the first step you got to do? Divide by 16. Yeah, divide by 16. So thankfully we don't have any fractions down here now, right? There you go.
you want us to find the folks, whatever.
Oh yeah, everything we did here.
Well, that's it.
Oh yeah.
Okay. So, it'll be this, yeah? For the folk side.
Yep.
But that gives me some of that. I'm gonna take the square root of that. Oh, 6.
No, wait, not 16 squared. Sorry.
Oh.
Yeah, it's 4 squared. Yeah.
Oh.
That is already 8 squared. So your denominators are already the squares of those. Yeah.
Oh,
So a
okay.
little bit better. Otherwise, you might have would have been outside of our
I was like, what?
ellipse. Yeah.
So that's a long one. Maybe it's really good to become clear.
No, no, it's gotta be 1. And don't even. The whole reason I was talking about that was just explaining why
Yep.
you just have to look at the top.
Where's your folk points?
16 squared is 4.
Somewhere on there.
4 and 15. If that was 0, this would be 0. The x could be something. That'd have to be 1, so that would be nothing like for this guy. But don't even think about that.
I like this stuff.
My
This is my
explanation for
favorite.
why you just look at the bottom. Yep.
See, look at this, I can
Be
control
careful
it.
here.
Whoa.
So like a is 4.
Whoever's gonna watch
So then a
it,
squared
6
is
if I can
16.
move it.
Really?
Oh, let's see.
Right.
Oh, I'm just getting invented here now.
Yeah.
Alright, so there's your C, so you can build your foci. And the foci are always on the major axis. Kind of makes sense. Right, so which one's going to be my major axis this time? X. Got a bigger thing underneath it. So then I go out how far?
3.87.
8, 7,
Well, okay, that's for this guy. To
Yeah.
actually graph the ellipse.
4.
Just go out 4, yeah. Negative. And then verse. I go out how far on the y-axis?
1.
1. Alright.
And then draw that.
So now I'm allowed to have the answer look like Stewie's head. So Stewie's head is Peter Saddle. And then the foci are going to be 3.87, so roughly, I always just put an X where they are.
Yeah.
Explains why it's really skinny, because I'm pushing those foci way out. Okay. Not too bad. So ellipses, let them be nice, right? When I get an ellipse problem, oh, thank God. Okay, good. So let's talk about hyperbolas. And before I get too far, have any of you ever been? Oh, yeah.
Do they know the foci between Earth and Sun?
Oh,
It looks.
how far off this? Yeah, they do. They know how. I don't know off the top of my head, but they know how far the sun is off center. You mean like?
Yeah.
Yeah, they do. They know the exact equation for the approximate equation because we can't handle all the variables involved. But yeah. In fact, I wrote a Fortran program a long time ago that modeled the solar system based on gravitational forces, and you let it run for thousands of years forward, let it run for thousands of years backward, just to make sure that it was written correctly. And I never quite got them to get right back to the same position. It's too bad for me. I got close. Nobody left. I didn't lose Pluto, right? It's a gust to lose Pluto. Okay. Has anybody ever been? I still haven't been to one of these places, but it's called a whispering room or a whispering gallery.
Oh, where you like whisper in one area and
So it's interesting about elliptical shaped rooms. If you're at one focus and you say something, it'll always bounce back to the other focus. All of the sound waves or whatever will always come back to the other focus. Bless you. So that's why if you go to somewhere, it's a whispering gallery. I know they have one up in, well, I say up in D.C. because of my brain. I was suddenly back in Virginia, over in D.C. I think they have one somewhere here. I don't know. But if you stand here and somebody else stands there and you say, even though the whole room is full of people, they'll hear you here. It's crazy. Because it all constructively interferes and comes back together here, and they can hear you just as well as if you were standing right next to them. I still haven't experienced this personally. Yeah,
I have.
You have?
It's like the weirdest thing. We were doing, me and my dad, we were doing like a trade show. And we were sitting on one side of the room, and on the other side of the room there was this guy who had this really low voice, but the whole time it sounded like he was standing right next to us. And we kept looking around like, where the heck is he?
So they had the show in an elliptically shaped room.
It was like a museum, so it was a big elliptical, it was an elliptical shaped room. And he was on one end, we were on the other, and the whole time it sounded like he was right next to us.
That's cool.
It was crazy.
I like it.
We couldn't figure out why.
That's could be why.
Yeah.
Yeah.
Isn't that also possible with two travelers?
Oh yeah, there's a lot of other ways you can do that. If you're a sound engineer, you can go into any theater and you can see all the different ways they try to. In that case, you're trying to dampen other sounds, and you know. So there's a lot of different ways you can achieve this kind of effect, but only an elliptical shape has this perfect. Everything always comes back to the other focus. It's kind of cool. Okay, and that kind of looked like the definition of an ellipse, right? So it's kind of related to that. So hyperbolas. I want to focus on these guys. Yeah, sorry. I didn't do it on purpose. So they're going to have this minus in the middle. And I'm just going to focus. Again, sorry. I'm just going to look at the real nuts and bolts of graphing these things. Right? So I'm leaving. They have the whole derivation of the formula in the book. I'm going to let you look at that if you want to. Considering time constraints, I just want to focus on how to graph these things. So what's really weird to me is, let's start with a nice one here. Okay. So if that was a plus, it would be an ellipse. You know, if you did it really quickly in the x direction, it would go out 3, and the y direction would go out 2. So look, you know, something like that. So what a hyperbola is going to do is it's either going to be up here, and that kind of feels like the relation between sine and cosecant, for example, right? Mm-hmm. Or it's going to be out here. So it's either this pair or that pair. So I always imagine there's always an associated imaginary ellipse in the middle of any hyperbola, right? Now, what determines whether it opens this way or that way is which one is not negative. So if I try to make x 0, what happens?
It becomes negative.
And I get what kind of answers for y?
Negative.
Come on, think about it. I get
Negative.
y squared equals negative 4. If I have y squared equals negative 4, what kind of answers am I going to get?
Irrational.
Worse. Yes, complex. Right? Do you guys see that?
Mm-hmm.
Yeah.
There are no... What? Y-intercepts.
Mm-hmm.
So that tells me that's exactly why if the x is the one that's positive, it's going to open this way. Because there are no y-intercepts.
Yeah.
But these x-intercepts actually work. So if it was negative and plus, if that was a positive one, it would have been this upper and lower one.
And it would actually have y-intercepts.
So, see, and it would actually have y-intercepts and not x. Exactly. So let that be simple. Let that part be really easy. The one that's not negative is the one that it actually sits on. It's going to sit on the x-axis because that's the one that's not negative. Right? Be really, really careful that I'm doing something evil like that. That's remarkably evil. I don't do that. Do you guys understand?
You have to divide by
Because
negative.
it's not a 1, you have to divide by negative 1, and people just do the whole thing before they realize that. Okay, cool. Now here's the beauty of hyperbolas. Instead of drawing an ellipse, of course, it's not going to work. What I do is, and to be a little more precise than this ellipse, if I drew a rectangle where the ellipse was, so let me make this a little bit bigger because I like this idea. So normally I can consider there's like an imaginary ellipse, and then I got we'll just focus on this one because it's what it is. If I draw a rectangle around this ellipse to be exactly the same length and height, You guys semi with me here?
Mhm.
Then that's kind of like what guides this guy. Because going through the corner, if I go through the corner of this, so I've drawn this ruler. That's what that's like an asymptote. That's what I follow as I go out. That's really cool. So constructing this rectangle is as easy as drawing an ellipse. I just go out as far as it tells me to. So how far am I going to go out for this rectangle in the x direction? 3. So there's that.
And then 2.
And then 2 in the y. So then the rectangle is going to look like this. So on the handout and in the book, they tell you how to get the equations for these asymptotes. What's really funny to me is you can get them afterwards directly. Draw your little rectangle. Go through the corner of this with your asymptote. So can anybody tell me what the equation of an asymptote is going to be? Equation like this. It's going to be plus and minus of this, right? So what's the slope?
1 over 1.
2 over 3.
Of 2 over 3, yeah.
Yeah.
Which in this case would be, B over A. And let me make sure you understand this is again why you really don't care about what you call A and what you call B. Slope is y's over x's. So whoever's with the y's on top and whoever's with the x's is on the bottom. It's that simple. Let it be that simple. The book is all B and A and B, and they almost have to be for general, but you just, whatever's with the y is up top, whatever's with the x is on the bottom. You don't even have to do that, though. You can just get it after you draw your rectangle.
Yeah.
Now, if this would have been y squared over 4 minus x squared over 9, this would have been the answer, but of course it's that. So this is the answer. So everything that's dotted is not really there, of course, right? They're just guiding me to draw this. So those are truly asymptotes out there. And it's kind of like what they had on that picture that I've lost now of the hyperbolic orbit. They had those asymptotes sitting there. I don't know if you remember that. Okay. And then here, you've got your imaginary ellipse sitting in here. Okay. So let's... So the foci?
Yeah,
What's up?
that's what I was going to ask.
Just say if we have a larger parabola, we'd have a bigger box, right?
A large ellipse? To make it fatter?
Yeah.
Yeah, it's to make it fatter. If I took this down, then this would be a smaller slope, and if it was up here, it'd be fatter. To make this fatter, you have to open it up, right? So if the ellipse, I'm not going to go that far. You can think about if the ellipse is there. If the ellipse is there, what it means.
Yeah.
You can still graph it without knowing that. That's a good way to think about it. I'm desperately trying to get you guys to try one on your own here now.
The focus point.
Oh yeah, the focus. So in this case, what's the formula for that?
A squared plus B squared equals C squared?
Yeah. Because the hyperbola has a minus in it already, so this one's allowed to have a plus.
And this one doesn't matter. Big first, little.
Yeah, because you're adding. Who cares? Yeah.
And it makes sense that it's on the outside.
Beautiful. It makes sense. It's bigger now than either A or B because it's got to be on the outside. So it's still that curve is curving around the focus.
Yes.
That idea still holds. So it's going to have to be out here or out there. For us, it'll be out here. So you get 9 plus 4, square root of 13, which is roughly
3.6.
plus 3.6. 1, 2, 3, 4. So it'll be right there. Don't make it a point, sir. 3.6 there. That makes sense, right? It's like we were talking about earlier. Push that bad boy in, it's going to pull it out, it's going to go, oh. Whatever sounds they make, I have no idea. So thankfully the textbook does do the rectangular method, which is always nice. So very quickly, just tell me, see if I can do this. No, Jeff, you want to hyper?
First divide by 81.
Yeah, good. So first divide by 81. So then how would you construct your rectangle?
Yeah.
X is 9, negative 9.
Good, X will be gonna be 9,
And your Y is
9, and Y will be
3, negative 3.
3, negative 3.
And you know it's opening.
I put those there because I know, yeah, I kind of get a
Gonna
little
go
bit.
this way.
It's opening left and right again here. I'm sitting on the x-axis because x is positive. Cool. So then these will actually be, they are still called the vertices, which is nice. Vertices for these hyperbola pieces. And then I draw in my rectangle.
Y equals 1.
And then I put in my asymptotes. Yeah, so then you can give me the equation afterwards. You don't have to memorize the little B over A or A over B business. It's just going to be,
3 over 9.
yeah, so the 1/3 x. And you just got to get the slope, and then you've got it. Now what a section 11.4 does is it takes all of what we just did and it adds one last step. You would do all of this, and then it moves it.
Up, down.
So it wouldn't just be that, it would be maybe x minus 1 squared minus y plus 4 squared. So it would move
Left
One.
one.
up
Oh, sorry, right one.
over 1 and down 4. So you just move this over 1 and down 4. That's all section 11.4 does. One extra step. Oh, test. Practice test.